So we have our givens. We have an open tube manometer, and inside the manometer there is liquid mercury. So we should first write a conversion. 1 millibar is equaling 100 pascals. That's just a conversion. And then they're asking us for the absolute pressure at the bottom of this manometer. So essentially, if we are finding absolute pressure, this is going to be P equals P sub O, which is atmospheric pressure, plus the density of mercury times the acceleration due to gravity times the height or the depth of this manometer. Here, it's going to be 98,000. Again, PO is simply going to be 980 millibars. And we need to convert this into pascals. So 980 millibars will become 98,000 pascals, plus the density of mercury being 13.6 times 10 to the third kilograms per cubic meter, times 9.8, the acceleration due to gravity, times the full length, rather the full depth of the manometer, being 0.07 meters. We can write down y1 and y2 here. Okay, and we've converted from centimeters to meters. And then this is going to be 1.07 times 10 to the fifth pascals. And then this is going to be for part A. So for part B, they're asking us what's the pressure at a depth of 4 centimeters. So it's going to be the exact same calculation, except when we're, instead of using y2, which we used here, 0.07, we're actually going to use 0.04, or 4 centimeters, 0.04 meters. So it would be, again, 98,000 plus the density of mercury times the acceleration due to gravity times the depth. And here they want us to use 4 centimeters, or 0.04 meters. So for part B, the pressure is going to be 1.03 times 10 to the fifth pascals. And this will be for B. So now they want us to see the absolute pressure of the gas within the container. So here the depth, the height that we're going to use is actually going to be y2 minus y1. And this is going to be 0.07 minus 0.03. And of course, this will be equal to 0.04 meters. Notice that this value is the same value as over here we used in part B. And all the other constants are going to remain the same. The atmospheric pressure doesn't change, the density of mercury doesn't change, and the acceleration due to gravity does not change. And we have the same height because in part B they're asking us for a depth of 4 centimeters, and then here they just asked us the absolute pressure of gas in the container, y2 minus y1 being 0.04. So for part C, because all these constants are the same, we find that the pressure is going to be equal to the pressure found in part B, 1.03 times 10 to the fifth pascals. Now, D is slightly different in the sense that they want the gauge pressure. So the gauge pressure is actually defined as the pressure of the hydrostatic pressure minus the atmospheric pressure of 980 millibars. And this is simply going to be equal to the density of mercury times the acceleration due to gravity times the the height. Here, the height is again y sub 2 minus y sub 1, 0.04 meters. So plugging in for our constants, we have 13.6 times 10 to the third power times 9.8 acceleration due to gravity times 0.04. And we find that here the pressure is going to be 5.33 times 10 to the third pascals. So again, this would be the final pressure. This would be the gauge pressure of the gas in the container. This is the absolute pressure. C is the absolute pressure of the gas in the container. B is the absolute pressure at a depth of 4 centimeters. And then P is, rather, part A is the pressure at the bottom of this manometer. And that's the end of the solution. Thank you for watching.